The second part of our look at stereoisomerism deals with what are known as enantiomers and the concept of optical activity. Okay, this occurs when a chiral carbon is present in a molecule, and a chiral carbon is one that has 4 different groups bonded directly to it. Okay, this results in some often unique reactivity, especially in biological systems, such as the thalidomide tragedy that we learned about with the pharmaceutical dilemma activity. Okay, the thalidomide tragedy, remember, was one that saw a drug prescribed to pregnant women for its beneficial anti-nausea effects, but also had an unknown teratogenic effect at the same time. Okay, so enantiomers are molecules that are non-superimposable mirror images of one another. So consider the cartoon molecules shown on the screen. They appear exactly the same, but they can't fit one over top of the other, much like your hands. So I'm going to say take a moment and draw 1 amino ethane 1-ol and locate the chiral carbon. So the carbon that has 4 different things bonded directly to it. Okay, you may want to pause this. Shown here we have 1 amino ethane 1-ol. Okay, here's the chiral carbon. All right, you can see the 4 different groups, and I built 2 models here. There's nothing I can do to either of these models in terms of rotating them that would allow me to convert one of them into the other, or for either one of them to appear in the exact same orientation as the other. Okay, these are what are known as enantiomers. Okay, enantiomers are often labeled with the terms R and S in front of them. Okay, so what does this all mean? Enantiomers, as in the cartoon molecules shown on the screen, all right, are non-superimposable mirror images, and the best example of where this becomes sort of an issue in terms of reactivity would be the, let's say, makeshift protein model shown here. So the protein receptor shown on the gold ball there has a specific arrangement that a molecule would need to fit into it, and you can see the cartoon, even though it has the same groups, can't be rearranged to fit into the appropriate holes. So these are the same but different. All right. Now, a solution that sees both enantiomers is known as racemic. All right. But oftentimes in the biological sense, only one of the 2 enantiomers will be present. This leads to differing reactivity potentially in a biological system when a chiral center is present or introduced. So now, how can we differentiate between enantiomers? All right, we can use what's known as a polarimeter, which essentially passes plain polarized light through a sample of the molecule, and the light will actually be rotated to the left or to the right depending on which enantiomer may be present. All right, this is can be demonstrated here with the thalidomide example. The S enantiomer is the teratogen, while the R enantiomer was the sedative, and these 2 can be separated, and we can differentiate them quite easily with the polarimeter. The problem with thalidomide is that it's actually the body converts the R enantiomer back into the S enantiomer, so it can no longer be used in pregnant women. Okay, the other manner in which we can differentiate between enantiomers would be through what's known as a reaction with a chiral auxiliary of some sort. All right, this process of producing only one enantiomer is actually known as asymmetric synthesis. It received the Nobel Prize in 2001, and is essentially the result of the thalidomide tragedy. It produces only a single enantiomer from basically reacting with some sort of biological molecule that enforces the handedness on the compound being synthesized.